Hi there. We want to continue our discussions about electrochemistry today. We're looking at last time we looked at sections, looking at the OpenStack Adams First Second Edition book. We kind of did sections 16.1 and 16.3 and 16.4. For the most part. We're now going to kind of look at 16.2 and 16.5 and 16.7 for the most part. Looking here, we have a couple of images from the book that I've got for you right here on screen. And the images are the same reaction. They're just done a little differently. So in 16.2 over here on your right, we've got a copper wire that's being put in an aqueous solution of silver nitrate. And we see over time, so this is time going along this way. We mix them together and then more time goes that way. We clearly see a change in that image. If I zoom in here a little bit, you can see that the solution has gotten blue. That's characteristic of the dissolved copper ion. And you could even sort of see some silver. It's kind of fuzzy there, but you can kind of see a little bit of silver growing in on that copper wire. So this reaction is silver nitrate in aqueous solution plus copper solid is going to copper nitrate and silver metal solid. That's aqueous. It's a redox reaction. The silver is +1 here. The copper is 0. At that point, it's +2 here. Silver is 0 here. So those are our oxidation states. The nitrate ions are just spectator ions. So our reduction process is that we give up 1 electron here. I'm sorry, we're gaining 1 electron. It's a reduction. Our oxidation, which is from here to here, is that we're giving up 2 electrons. So to make that work out, we have to do the reduction twice. So 2 of those and 2 of those. If we think about those half reactions, the oxidation half reaction is basically leaving out the nitrates, going to be silver plus an electron goes to silver solid. And our oxidation half reaction is copper metal goes to copper +2 electrons. And okay, so this is the oxidation half reaction, and this is the reduction half reaction. Now, over on the left-hand side, we see what's called a galvanic cell or a voltaic cell. And it's we've separated the reactions into 2 different chambers and 2 different beakers, basically. And by doing that, what we can do is we can exploit the flow of electrons. So what happens to these 2 electrons that are given up by the copper? Those 2 electrons go through the copper metal and through the wire and over through either something that's exploiting the electron flow, or just a voltmeter that's telling us what the voltage is. And eventually those electrons get to the silver ions over here and combine with the silver ions and create silver metal that's going to plate out here on this electrode. That is a silver cathode, so it looks just like the cathode. We have in the middle of this cell something called the salt bridge, and the salt bridge is an ionic solution, usually often a kind of a gelatinous one, and the point is just to let charged ions move to maintain charge. So since electrons are leaving over here on the left, they're negative, so negative things, the nitrate ions flow over from the salt bridge to balance the charge. So that completes the circuit and lets the circuit flow all the way around. If we don't have the salt bridge there, nothing happens. I've seen things as simple as pieces of paper be used that are soaked with some solution be used as a salt bridge. I've even seen some examples where your body is used as a salt bridge. It's kind of a cool demo. Now, there is a thing called cell notation. And one of the objectives for you to get is to be able to go from cell notation to a description of the reaction, to a calculation of the cell potential, to maybe a diagram of the galvanic or voltaic cell, or the electrolytic cell, as we'll see later. So the cell notation, always you have the anode reaction first, then you have two lines signifying the bridge, and then you have the cathode on the right hand side. And I can move this down a little bit, I think. Let's see if I can get that to move. Give ourselves a little more room here. So it's always good to remember, in redox chemistry, we can use things like Leo goes Gur and things like oil rig to remind us that oxidation is loss, reduction is gain, loss of electrons is oxidation, gains of electrons is reduction. There's a way to remember what goes on in the anode and the cathode. If you look at reduction, there's a C in the middle of that, and you could imagine cathode going there. In oxidation, there's an A in the middle, so you can imagine anode being a crossword with oxidation there. So oxidation occurs at the anode, reduction occurs at the cathode. Another thing to remember is that the cathode is named because cations go to the cathode. So it means the cathode's actually negative. Anions, which are of course negative, cations are positive, flow to the anode. So the anode is positive, and the anode's where the electrons are leaving. If we look up here, the electrons are leaving here in this this copper anode, and so this is if the electrons are leaving, that's the oxidation, and that would make the anode feel positive, and you see over here the anions moving in that direction. And then the silver cathode is getting a negative charge, and the positive ions like silver and sodium are moving towards the cathode. Now we want to just write this cell notation down, and we'll see with a few examples here how to do this. So let's go up here and take a look at this. So our cell notation, we're going to write the anode first, and the anode is a piece of solid copper, and in solution next to it, so a vertical line indicates that you've got a change in phase there. So going from a solid to solution, we've got copper 2+ ions. We don't have to list the nitrate ions. Then we have the bridge. And then over on the anode side, the cathode side, we've got silver ions in solution, and then we have a silver electrode. So this would be the cell notation for this cell is described right there. And I always say it's A, B, C, anode, bridge, cathode. You might see added to this descriptions of the concentrations of the things that are in solution. We'll touch on that a bit later. Let's just review the calculations here if we are trying to calculate the cell potential for this. So we're going to go over and look at our reduction potentials. And we had silver plus going to silver, so this one is 0.796. So this reaction is written as got a half reaction potential of 0.796 volts. And then looking for our copper value, we're looking for copper metal. Since these are reduction potentials, we're going to look for copper metal going to copper plus 2, or copper plus 2 going to copper metal. And so we have this one right here. Copper plus 2 going to copper metal is positive 0.34. If we go back and look at this one, this is the reverse of that. So our E naught of oxidation here is negative, what I say, 0.34 volts. We flipped the value around because we reversed the reaction, and so if we calculate the cell potential for the COX, or so E cell, maybe I'll get us some more room here. Let's do it down here. E cell, E naught cell, standard cell potential, is going to be equal to E naught oxidation plus E naught reduction. That's going to be negative 0.34 volts plus positive 0.796 volts. So that comes out to, find my calculator here, it's going to be something around 0.45, looks like. So I'm going to say 0.796 minus 0.34, and sure enough I got 0.456 volts, and again that's positive, which means that reaction is thermodynamically favorable at standard conditions, which is what the naught means. I do want to point out that some people refer to EOX as negative E naught reduction anode, and the E naught here is referred to as E naught reduction cathode, because that's exactly what we do. We go to we figure out what the half reaction is for the anode. We then change the sign of that because the anode is occurring as an oxidation. So what you'll see sometimes is you'll see folks put these together to give you E cell, and that might be written so that you're subtracting, so E naught reduction cathode minus E naught reduction at the anode. It's the same thing, it's just confusing. I prefer that method, largely because it's the way I learned it, but also because I think it's unnecessarily confusing. But you will see people do that sometimes, so you might encounter that, and you should be aware of it. All right, let's look at another cell. So here is another cell, and this cell, again, I'm just pulling examples from your book, so you can certainly look in the OpenStax book and find where these figures are and have an understanding of what's going on here. So what's going on here is we have magnesium going to magnesium plus 2. We have iron plus 3 going to iron plus 2. Now you can't make an electrode out of iron plus 3 or iron plus 2, so what we have here is a inert platinum electrode, okay, and we're going to note that somewhat differently. So our cell notation for this is going to be Mg electrode, Mg2 plus in solution, our bridge, then we've got Fe3 plus and Fe2 plus in solution, and we have an inert platinum electrode. So looking at the half reactions here, magnesium goes to magnesium 2 plus 2 electrons. That's the oxidation half reaction. E naught for that we'll get from the table in a minute. On the reduction half reaction, it's going to be iron 3 picking up an electron and giving us iron plus 2. So let's go look those up on our diagram here. So we're looking for iron and magnesium. We'll probably hit iron first. So iron 3 to iron 2 right here. Positive 0.771 written that way. So this one is positive 0.771. These are all volts. Then let's go find the magnesium one. So going back to the tables and going down alphabetically here, looking for magnesium. And magnesium ion, +2 ion, picking up 2 electrons and becoming magnesium is negative 2.372. What we're doing is the opposite of that, so it'll be positive 2.372. And you may notice that's a pretty large voltage compared to what we've been seeing. So our overall reaction potential, remember, even though we have to double the second reaction to get the electrons to be equal to each other. So if we get to the reaction, it's Mg plus 2Fe plus 3 plus the 2 electrons that cancel out go to Mg 2 plus 2 Fe plus 2. In electrochemistry, we don't multiply those half reaction potentials by whatever number we multiply there. We just simply do the addition. So 2 and 1 is 3, 7 and 7 is 4, carry my 1, 7 and 3 is 10, 11 with that carried 1, carry that 1, I get a whopping 3.143. I apologize, I don't have this at a good angle. 3.143 positive. That is our E0 for this cell, which again is a very, very spontaneous reaction. So I wanted you to see that example where you have an inert electrode and then we have, you know, 2 reactants in that reduction half reaction cell, so in the cathode in this case. And there's no reason you have to have that on the cathode side. We could see examples where you have that on the anode side as well. Alright, moving down a little bit, I wanted to show you an example of a gas electrode. That's what's going on over here. We have a gas electrode. We have a platinum electrode here in the middle. And what we're doing is we're able to pump hydrogen gas in or out, depending on which way the reaction's running, in that electrode and into solution. So, and this is in fact a famous electrode. It's called the standard hydrogen electrode, and it's used as a reference electrode. So what's going over here on the what appears to be the anode side of that, if we the electron flow is correct, is we have so on the anode we have H2 going to 2H plus, and each one of those is giving up an electron. And at the cathode, and I'm getting that from the electron flow is what I'm looking at to make sure which way it's going. Normally I would look at the potentials, and we'll calculate the potential and see if we've got it going the right way. So over at the cathode I have copper plus 2 going to copper. That means it's picking up 2 electrons. Our electrons are balanced out, so it's just going to be H2 plus Cu plus 2 goes to 2H plus Cu. The 2 electrons cancel out. If we look up our cell potentials, so pull the table here, let's go find hydrogen. And what you're going to see here is looking for hydrogen to, yeah, okay. This is essentially 2H plus. And then the 2H2O are assumed for that. They're using the hydronium ion instead of H+. This is the reference where we set the 0 point. That's why it's called the standard hydrogen electrode. So that one's going to be 0. And again, all they've done here is they've written the version of this, instead of writing hydrogen ions as separate ions, they've written hydronium ions, which is a hydrogen ion plus water, just like we talked about in the acid units. And then we're looking at copper again, right? Let's go look at copper. I think I can remember 0 for that one. Let's see up here. Copper. Okay, is it alphabetical by symbol or alphabetical by name? Copper, there we go. Here's our copper value again, so that's positive 0.34 written in that direction, right? Right. So let's go look over here. So this is 0. This would be positive 0.34. And so 0 plus 0.34 is positive 0.34. What this is, in fact, is a device that one could use to measure that reduction potential for copper plus 2 going to copper. The cell notation for this, we're going to have our platinum inert electrode. We're going to write our hydrogen gas, which again, phase diagram there, phase line for that. We've got hydrogen ions, so that's all the anode side. And then on the cathode side, we have copper 2+ ion in solution and a copper electrode. So that's how you write the cell notation for this this particular example. All right, so here is another example. We moved a little further back in the book now. I think we're now looking at this is in the 16.7, the electrolysis section. And so this is, we're dealing here with molten sodium chloride, which is a pretty unusual thing, but molten NaCl, that just means NaCl, not AK, liquid. Okay, so this isn't salt dissolved in water. This is salt heated up enough that it's melted. So this is really hot, and you know, if you're like me, you've probably never seen this. And you may say, why is this important? Well, it's important in a process that's called the Downs process, where we produce sodium and metal and chlorine gas, which both have important applications in industry and also laboratory chemistry. So, so how would we write the cell diagram for this? Well, they say here you typically use iron cathodes and carbon anodes. So which one is the cathode and the anode? Well, chlorine minus is going to chlorine gas over here on this side and giving off 2 electrons. Loss of electrons is oxidation. This is the anode. And so that is a carbon anode. And you say carbon, well, it sounds weird. Well, it's carbon, solid carbon. It's actually graphite. Looks sort of like a black piece of plastic. I've seen carbon anodes a lot. So we have our carbon inert anode. We are generating here chlorine gas. They don't show a gas collection device going around it, but we could have had one here where we're getting Cl2 coming out of that. Then our bridge here is this porous screen that's just in the molten sodium chloride. And over here on this side we have sodium liquid, and I guess I should say liquid, not aqueous. Again, we're dealing with very, very different stuff. And that is becoming sodium solid. And that is happening on an inert, for this reaction, iron electrode. So slightly more complex cell notation. We wouldn't usually notate it as graphite, but we might. I mean, you're just not going to use a diamond electrode. That's kind of the range of carbon possibilities there. But that's the potential for this. calculation of this is going to be kind of an estimate, because we're really, if we tried to calculate the cell potential for this, all these values that we've got over here in this table of reduction potentials, these are all in water. And this is not in water, it's in molten sodium chloride. I don't know off the top of my head if that's if there's a table of values. I'm sure there probably is somewhere, but that's a very different thing than the values in water. Now, but we're leading up to talk about a water example here, so I wanted to take this one, and I'll move it up here. This is the electrolysis of water. And you may say, why are we jumping to that? Well, in a minute we're going to be looking at sodium chloride in water, so we need to think about this. So this is a diagram of an experiment that actually I think was a pretty important experiment. It's sort of the experiment that led Avogadro to come up with the idea that the volume of a gas and the number of atoms or molecules in that volume might be related. If you pass a current through water, so you have your voltage source down here, you've got your anode and your cathode, and those are inert anodes and cathodes. I don't know what they are in this case. We'll make something up in a minute here. Let's say they're platinum. So we have a platinum cathode and anode on one side, and a platinum over there, inert anode. What's going on the anode side is H2O is going to O2 gas, and on the cathode side, the reduction reaction is H2O. Well, I should write it the other way. Hydrogen gas is being produced from H2O, and this is going to turn out to be a non-spontaneous reaction. Sometimes we talk about whether something's happening in acid solution or basic solution. This is happening in acid solution. You see sulfuric acid is here. We're not going to dwell on the difference between acid or basic solution type problems, but if you encounter them, you can probably deal with them. It just means we pull values from different tables. Okay, so what we got going on here again, so our oxidation half reaction is going to be H2O going to O2. Now, what else is going on there? Where are the H's going? Well, the H's, remember, the H's are +1. The oxygen's -2. The oxygen's going to 0 here. We need 2 of these because we've got to have 2 oxygens. Each one of those oxygens is giving away 2 electrons, so this is 4 electrons. And then where are those hydrogens going? Well, they're going to be 4 H pluses, and if we write that as hydronium ions, it would be 6 H2O goes to O2 plus 4 electrons plus 4 H3O pluses, I think, where 2 of the water molecules became the oxygen, and the 4 protons that got added to the remaining 4 water molecules. On the redox side, we have got H2O now going to give us hydrogen gas, and that's going to give us I'm going to assume that's going to be O2 minus there, so we're going to be picking up 2 electrons to make that process go. So that's what I think is going on in those half reactions. Now, if we go back and we look at the table for that, let's see. What we get is that what we get is, so what we're being asked to think of this as, I'm looking at the book here, this one's being thought of as 2H plus because of the acid component, right? plus 2 electrons going to H2 gas. All right, so if we look up those cell potentials, and I'm going to cheat, and pull those off of a side here without carrying over to the table. We'll look at these. This half reaction right here, whichever way we think about it, is positive 1.229 volts. This half reaction is, let's check that one in the table. I've got confusing values here. All right. So let's look at the water, which is going to be under H. So the water producing oxygen in acid solution. Not seeing it on my end. Maybe I'm going to pause for a second. All right, so since oxygen is a product of an oxidation process, and what we're looking at, I'm looking for oxygen as a reactant here. So instead of looking under water, I had to look under oxygen. And so that value is 1.229. But if we go back and look at our process here, we've turned that around. So this is going to be negative 1.229. The other value here, the hydrogen ion, going to H2, that's the standard hydrogen electrode, so that's 0.0 volts. So our E naught for our cell is going to be negative 1.229 volts. And remember, that negative means this is not thermodynamically favorable, which means that we have to put energy in. And that's not startling result. I mean, you know that if you have a glass of water, that hydrogen oxygen gas aren't bubbling out of it. The way we produce the hydrogen and oxygen gas is if you have to put current through that. You have to put an electrical current through that. So, and it's got to be 1.229 volts worth at least. Okay, now, so we're going to look at the case where what if I have NaClAQ and I do what's called an electrolysis. And again, what we got here, this is an electrolytic cell. Now, let's just define that. Electrolytic cell. That means it's one of these ones where we have to put energy in. Cause that reaction to happen. All right, so let's think about salt water, and so we've got two electrodes in here. We've got I'll use the symbol for a battery here. Generically, we've got something providing electrical energy to go through this, and in this thing we have water, and we have Na plus and Cl minus, right? So we've got salt water. What's going to happen? Well, we have to think about all the possible processes, right? So what's reasonable to happen to the sodium? Well, the sodium could pick up an electron and go to sodium metal, right? That's a known process. You've never seen sodium plus 2 or plus 3 or whatever, so sodium ion's not going to lose electrons and get oxidized. It's pretty much the only thing that could happen for sodium here. So for the E naught for this half reaction, let's just go look that up. Again, we're looking in water, so this makes sense. So I'm looking for sodium, and it is alphabetical by symbol I see here. So that's negative 2.71. Negative 2.71. Not a very probable reaction. These are all volts again. What could happen to chloride? Well, what's most likely to happen to chloride is that 2 of them are going to become Cl2 gas and give up 2 electrons. And so let's go find that one. So reduction potential, we're looking for Cl2. So go back to the up here. So Cl2 plus 2 electrons going to 2 chlorides is positive 1.36, we'll call it, right? It's obviously a very studied reaction because they know the value out to a lot of decimal places there. But let's call it 1.36. So if we go back and look at what we're doing, that's the opposite of that. That's going to be negative 1.36 because, again, this is an oxidation half reaction. Looking very unfavorable. Now, the thing we have to think about, though, is also we got water in here. What could water do? Well, water could do exactly what it did up here. We could have water become oxygen. Okay, so 2H2O goes to O2 plus 4H plus and plus 4 electrons, and it's negative 1.229. Negative 1.229. And then we could have 2H plus 2 electrons go to H2, which is 0. All right, so if we look at our reactions here, this one and this one are both ones that are reductions that could occur at the cathode. And these two right here are oxidations that could occur at the anode. And to figure out what's going on, what's going to happen, we're going to pick the most energetically favorable of each of these. So, the most energetically favorable that we're going to have is the at the cathode. It's going to clearly be the hydrogen reaction. The most energetically favorable at the anode looks like it's going to be water in this case, and so if this is in an acid solution, we're going to pick this one and this one. Remember, the more positive is, the more energetically favorable it is. So in acid, salt water, is not going to actually itself react. What we're going to have is we're going to have just the hydrolysis of water to give us, let's see, we're going to have to do this one twice. So 2H2O plus O2 plus 2H2, and our E naught for that is going to be negative 1.229 volts. So if you put electrical energy through a solution of salt water that's neutral or in acid, in presence of acid, you're not going to form sodium. You're not going to form chlorine gas. You're going to make oxygen and hydrogen. It turns out if you do this in base solution, and there's a nice discussion of it in the textbook about that, if you do it in base solution, you actually can then begin to produce some chlorine gas, which is how they do that in the chlor-alkali process. So in base, C book, but in base, what happens is 2 waters plus 2 chlorides go to H2 plus Cl2 plus 2 hydroxides, and the potential for that is negative 2.186 volts, which is the most favorable possible combination in. If you got multiple unfavorable reactions that can happen, the one that's going to happen first as you apply energy to it is the most favorable of the unfavorable solutions. All right, I wanted to talk briefly about this concept of electroplating, which kind of changes our gears just a little bit in terms of some calculations we can do. Here is a setup for electroplating silver onto a spoon. Of course, you're probably familiar with either jewelry or silverware that's been plated with a more valuable metal on top of a more common or less expensive metal. What we have to do to make that happen, in the best of circumstances like this one, we have a standard potential of 0, right? Because what's going on the anode is silver is going to silver plus 1 plus an electron. At the cathode, silver plus 1 plus an electron is going to silver. Without knowing those cell potentials, which you looked up before, E0 for the cell is going to be 0. So to drive this reaction, we're going to put energy in, and again, it looks a little silly to write it this way, but we're going to put energy in to drive this reaction forward. And the question that you might see is, if you have, for example, you run this reaction for a period of time at a certain current, how many grams of silver might be plated, right? So let's say if we run this reaction for 10 minutes at let's say 9 volts, okay, how many grams is plated out, assuming we don't run out of silver in the solution, or in the silver in the anode. Okay, what this is actually, although it doesn't look like it, it's basically a stoichiometry type problem where we're going to have to use a couple of tricks. So one thing you may remember, let's look at our equation sheet here. The Faraday constant, in addition to this joules per mole units, it also has the coulombs per mole. Okay, and then if we talk about amps are a coulomb per second. Do we leave that out? I guess I have to specify not 9.0 volts. Let's say the potential is not there. We're running it at let's say we're running it at 10 amps. I meant to do that. So that's current. Amps are current. Volts are potential. And if you haven't taken physics 2, current and electricity deal with current, which is volts, potential, which is amps, current, which is amps, which is the flow of electrons, potential, which is volts, and then the resistance, which is in ohms. So what we know here then, and we got some information, on the equation sheet here, is that 1 amp is 1 coulomb per second. So I can go back up here and say this is 10.0 coulombs per second. Coulombs are units of charge. And then we have in the Faraday constant a conversion factor between moles of electrons and coulombs. So 1 mole of electrons is 96,485 coulombs. So 96,485 coulombs per mole of electrons. That's the Faraday constant. And of course we can take 10 minutes and convert 10 minutes to seconds, right? 10 minutes times 60 seconds per minute. That will give us 600 seconds. All right, so let's see what we know. We know that we're running this. We want to get grams of silver. We know that we run it for 10.0 minutes at 60 seconds for every minute. Minutes cancels out. We know that we're running it at 10 amps, which is 10 coulombs for every second. So seconds cancels out. And we know that if we generate 96,485 coulombs, we'll have generated 1 mole of electrons. And then from our reaction, we know that for every mole of electrons that flow, we get 1 mole of silver. And then if we go to the periodic table, and I know I have a periodic table here somewhere. We go to the periodic table, we will see that silver, if I have 1 mole of silver, I have 107.9 grams of silver. So again, I got this from the reaction. This is the Faraday constant. This is the amps, written that way. And of course, this is the time we run this. And this is the molar mass from the periodic table. Notice nowhere on that is the cell potential. And that's what always threw me about these, is that we spend all this time in electrochem calculating cell potentials. When you hit this kind of problem, suddenly cell potentials don't matter. So 10 times 60 times 10 divided by 96,485 times 1 divided by 1, we don't have to do, times 107.9. We're plating out in this 10 minutes 6.71 grams of silver, which is quite a bit to plate out in fairly short time. I suspect 10 amps is a high current to run for this kind of problem. The other kind of problem I want to talk about is non-standard conditions. And you deal with these all the time. You deal with this all the time because you probably have a cell phone, and that cell phone battery runs down and you have to charge it back up. And you didn't realize it, but you're dealing with electrochemistry at non-standard conditions when you're doing that. So the equation, again, if we look on our formula sheet here, we have down here in the electrochem section, the equation looks like this, and there is this is common log here. This is natural log. For some reason, we got this on here in a way where the shortcut version is the version of the common log. This part is the at 25 degrees C part. That number is good only at 25 degrees C. So what it looks like, again, is that E, the non-standard cell potential, is equal to the standard cell potential minus RT over NF times ln Q, where Q is the reaction quotient of the electrochemical reaction you're running. N is the number of electrons transferred. So if you balance the redox reaction and you figure out how many electrons are being produced and consumed, the number that you get them the same, so you can cancel out that number, is the number of electrons that are transferred. F is the Faraday constant. T is the temperature in Kelvin. And R is the gas constant in energy units. And the shortcut is that at 25 degrees Celsius, RT over F is 25.7 millivolts, or 0.0257 volts. So the shortcut version that I normally would use is that E is E naught minus 0.257 volts over N times ln Q. That's with, really this I guess this is volts per moles of electrons, or volts times mole electrons I guess is what it would come out to be, because N is the mole of electrons, so that cancels out. The idea is that this part gives you units of volts. This part, of course, is unitless. And then, of course, this is in volts as well. So you can see cells, like let's go back and just steal one of the cells we talked about earlier today. So let's go up here and look at the first one we did. So up here, this copper-silver cell, we decided that the potential for the whole thing was positive 0.456 volts. That's our E naught. And our number of electrons is going to be 2, right? N equals 2. Because there's 2 electrons being transferred in the copper reaction, only 1 electron in the silver reaction, but we'll run it twice. So 2, N is 2, and the potential is 0.456. So let's go down here and use that one. All right, so N equals 2, E naught equals positive 0.456 volts. And again, that's for the copper plus 2 silvers goes to, so 2 silver ions goes to copper plus 2 silver solids, right? That cell are, as we said, copper 2 plus silver solid, and well, they actually, that example used a silver electrode. All right, now Q for this reaction, I'll write it that way. Our reaction quotient, remember that it's products over reactants. We take the concentrations raised to the power of their exponents. So this is just going to be copper 2 plus over silver squared. Okay. Now, if those are 1, standard conditions means that these guys would be equal to 1. If I do Q for that, Q is going to be 1 over 1 squared. That's 1. What's ln of 1? It's 0. So what happens in our equation then is that E minus E naught, or E equals E naught minus 0.0257. That's 0.257 up there, millivolts, over N ln Q. That's going to be 0.456 volts minus 0.0257 volts. Okay, I'm getting confused. Volts, not millivolts. Over 2 times ln of 0. Ln of 1. That means this whole term becomes 0. So it's just 0.456 volts. And so what that means is standard conditions, which are those guys, E is E naught. Kind of no surprise, but just playing that out. All right, let's say that instead we run this reaction for a little while, and the solution gets blue from the copper ion, and the silver begins to form on the copper metal. And we arrive at a condition where, say, the copper ion is at 1.0 molar, but the silver ion is at something like 1/10 of a molar. Right, so there was initially no copper ion, and silver ion in solution at maybe 1 molar, and over time the silver ion's gone down and the copper ion's gone up. The stoichiometry doesn't work out. I guess the silver ion would have had to have been 2.1 molar, not 1.0 molar initially. You can figure that out, I'm sure. But we have these conditions. What's the potential at that point? So E is going to be equal to E naught plus positive 0.0257 volts over our 2 electrons, or N, I'll put in here, L and Q. Alright, so that's going to be positive 0.456 volts minus 0.0257 volts over 2 times Ln. Now Q is, in this case, Q is going to be 1 over 0.1 squared, and so what's that going to be? That's going to be a big number, right? 0.1 squared is 0.01, and divide that into 1, you get 100, right? So now we've got Ln of 100. So if we take the natural log of 100, that's 4.6, and we're going to multiply that by 0.0257 divided by 2. That whole term is now going to be negative 0.059 volts. This, of course, this E naught here is still the same thing. So our potential is going to go down by 0.059 volts, which means that the potential is down to 0.397 volts at those conditions. So as we're running out of the reactant, we find that the driving force for the reaction, the energy we can exploit from it, is going down. The battery's going dead, if you will. So you may have questions where you have to calculate those. This, of course, is like the similar equation for delta G, that delta G is equal to delta G naught minus RT Ln Q. So it's a similar equation. This equation is known as the Nernst equation, N-E-R-N-S-T equation. To my knowledge, this equation, poor thing, has no name. I don't know why it doesn't have a name, but I've never found a name for it. Anyway, one thing you might deal with is what's called a concentration cell. I've seen those on test questions. All that means is that E naught is 0, that you have one of those things like the situation with the electroplating, where you've got, you know, silver plus silver ion going to silver plus silver ion, or silver ion plus silver, where we're plating the silver ion. E naught's 0. What's going to be different is the silver ion that are products, and the silver ion, in this case, that are reactants. And that would be our Q value there. And if that were separated then into cells, right, that would, to calculate that, we'd have to separate that into cells and have our silver source on one side and our plating going on the other side. Again, that's going to be in 2 different cells if you do that, but that's what that is. And then so E equals E naught plus RT over NF Ln Q just becomes E equals RT over NF Ln Q. You don't have to deal with the E naught part of it if it's E naught 0. And again, that's for a concentration cell. Okay, there's a lot more fascinating things to talk about in electrochemistry, but alas, we're not